Hi everyone. It's really exciting to be here. The last time I was in Pittsburgh was a really long time ago. I went to school here in Pittsburgh, the INI, so go Titans. And right now I live in New York and I never get a chance to come back and see everyone, so it's really nice to see all of you today. And so my name is Victor Dibia. I'm a machine learning GDE, and so what that means is that I spend some time writing articles about machine learning and contributing to the community and having nice little conversations and talks like this. And the rest part of my work, my day job actually, I'm a research engineer at Cloudera Fast Forward Labs, and so we're a machine learning research and development applied research group over New York, in Brooklyn. And so that's my day job, and the night job, it's a different story. And so at night, I pretend that I'm an artist, and then I spend my time using neural networks to actually try to generate art. And so, folks, here we are, and the title of my talk is Art and AI. And so here I talk about my work generating some African mask art using generative adversarial networks. And it's not an extremely technical talk, but the idea is to get everyone excited about the opportunities that kind of lie in this space. And so a little bit of a background on why art, AI, why is this particular intersection really interesting to me? And it's a little bit personal. I grew up in Nigeria, it's a country in Western Africa. And one of my fondest memories from my childhood was that once every year, typically in December, my family and my extended family, my uncles, aunts, and their kids will all have this trip back to a village. And during that process, we will spend time just like hanging out and going through a few activities. And one of the highlights of that event was something called the acrobatic masquerade dance of Eastern Nigeria. And so what happens there is that you'll see people dressed in interesting attires like this, and they had all these interesting masks, and they'll like do all these flips and acrobatic dances. And so as a kid, I was really fascinated by African mask art, and now as a machine learning engineer, this kind of work is one way to kind of explore that fascination a little bit more. And so one thing you'll notice if you've ever seen some African mask art, and so in the diagrams you see here on the right, these are two examples of masks designed in Africa. And the first one is something called the bronze mask from the Benin tribe in Nigeria, and the second one on the right is the Achokwe mask from Congo. And so there are a few things you'll notice about them out of the box. The first is that they're typically fierce, and the main reason is because they're supposed to represent some kind of deity or some of the ancestors or mythological beings that typically have power over humanity. The second thing you notice about them is they're pretty sophisticated, and so you'll see them in a range of materials from wood, from clay, bronze, iron, and they typically will have these really interesting, complex, patterns on them. The third thing is that they're surprisingly ancient, and so archaeological excavations and research shows that many of these masks date as far back as the 9th century BC, which is pretty interesting. And then finally, they're functional, and so as opposed to artistic pieces that are just consumed for their visual excellence, these things actually represent identity. And just like you will wear clothes and have accessories as part of a reflection of your identity, African mask art are actually designed that way. The other thing is that they represent communal memory, and so some of these masks represent things like planting crops, harvesting, wars, and all of that interesting stuff. And so they have this really interesting, rich background. And so why did I go ahead and do all of this? And so the first thing is, like I said, it's kind of personal. It's a way for me to bridge my interest in art, technology, and also express my identity and look at all that intersection. The second thing is, if any of you have worked with generative adversarial networks, you will see that there's this growing genre of artistic pieces that are created using neural networks. And the interesting thing is that space is typically dominated by classical European art. And so you see artistic expressions using data sets of images from Van Gogh, Rembrandt, and Picasso. And a project like this is an opportunity to kind of diversify that space. And then finally, as a research scientist working in the field of machine learning, there's all this really good work around creating really good generative models. And the data sets we have today are things like some really good data sets like Celeb A, Celeb HQ, and these can be really good data sets for evaluating the results of the new architectures that come out. And so part of this project is to, at some point when we understand the data set really well, contribute it as a potentially good benchmark for for benchmarking generated models. So that's kind of the motivation. So what did the results look like really fast? And so the image you see right here, it's an image of things that look like masks, but the interesting thing is that none of them are real. And so all of these are like examples of some of the masks that are generated using a deep convolutional generative adversarial network. And so this is an example of what some of the results from all of this exploration kind of looks like. Okay, so how did I go ahead and build this, this little project? And typically, what are some of the related fields that surround this area? So the first is generative art or computational creativity or code art. And so this is a fairly old and robust field. And so for people who have seen this, typically it's described as art that's in whole or in part created using some kind of autonomous system. And over the years, there's been some really good tools out there. So how many of us have used processing? Okay. And so processing is a basic programming language. It helps you generate patterns and art expressions. We've also seen things like P5.js. And so the interesting thing here is that tools like that, they're like basic programming tools. You have some kind of artistic vision, you write some code, and these tools can help you realize that vision. But neural networks take a slightly different approach. And so in this case, rather than actually having your rules specified, your data set becomes the primary input into the creative process. And so imagine I was going to generate some nice, really looking patterns of circles. If I was going to go the traditional approach, I would write some code and say processing that helps me generate all of that, put in some parameters and see what the results look like. On the opposite side, if I was going to use neural networks, the idea would be to collect a few thousand examples of circles, get the neural network to learn what that distribution looks like, and then sample from that distribution to create new circles. It's not really intuitive. It sounds like a lot more work, but it turns out that if the amount of work you want your autonomous tool to do is really complex and really complicated, for example, generating things like mask art, it's hard to really write rules for that, and so generative models are a really good choice for that. And so the process is typical, like any machine learning project. You start out with collecting your data sets, and in this case, the data set needs to be carefully curated, especially because it's a fundamental part of the process. The second part of it is related to training your model, and so here we use a generative adversarial network. In the example I'm going to show, I use a deep convolutional generative adversarial network. And then finally, there's some work to kind of evaluate, what results did it come up with? Do these results, do they make sense? Are they really novel? Is the network memorizing its input? All that good stuff. And so the first piece is data curation or data collection, which I guess is the best part of the process. And so do we agree that the data collection and cleaning is the best part of the process? Yeah, I see someone who really enjoys data collection. So we all know that for really good results, you need to have really good data, and this thing tends to eat like a huge amount of your time process. And so for this project, it was all around data scraping, in some cases manual image downloads. The next thing is to carefully hand curate every single image. And so here you're removing vector images. We want actual images of masks, and so we don't want vectors. You want to remove images that are incorrectly labeled. You want to remove masks that have nothing to do with Africa. And then finally, you need ways to identify and remove duplicates. And there are some semi-automatic ways to actually do this, but I don't discuss that here. So at the end of this really nice process, over a couple of weeks, I ended up with about 11,000 curated images, and that kind of became the nucleus for the experiments performed here. And the image on the right shows some examples of what some of these masks actually look like. And so the range is really diverse, and yeah. Okay, so now that we have our data, the next thing is we need to come up with a generative adversarial model and the goal here is to create something that tries to understand what what a mask would look like, the distribution of African masks, such that at test time or at generation time, we can get it to work with us to generate stuff that's new and novel. And so for that, I use the basic generative adversarial network formulation, and this stuff, I find it really exciting and really interesting. It's an arrangement of two neural networks that play a competitive skill game. And so it has two parts. First, the generator, and the second part is the discriminator. And so what the generator ends up doing is that it learns to map a noise vector of some specific length, and then map that to to the distribution of images. And so what happens is that it takes as input some noise, and its output is actually a generated fake image. And so that's the first part of the network. The second piece is called the discriminator, and it has one simple task. And so it takes in an image that's generated by, created by the generator, something that possibly doesn't exist. And at the same time, it takes in an image from the actual data set, from the real data set of real images. And its task is to kind of decide, is this real or fake? So real being that it comes from the actual distribution, and fake being that it's something that was synthesized by the generator. And essentially, the way this works is that at training time, for each image that comes in for the discriminator, we look at its prediction. Does it get it right, real or fake? And then we use that signal, we back propagate that, and we use that to update both the discriminator network, and we use that to update the generator network. And the idea here is that at the end of the training process, if everything works well, we have a generator that becomes really, really good at generating images that the discriminator can't tell apart. And finally, we have a discriminator that becomes really good at telling real from fake. And one of my favorite analogies here is the analogy of the thief and the policeman. And so we start out with this thief who really is really bad at his job. He's an amateur. He creates a painting. And right out of the box, the policeman can spot that, oh, this is a fake. This doesn't exist. You're going to jail. So the thief goes to jail. There in the jail, he meets the Godfather. And because the Godfather has like a really good network, he has people in the police department. He can tell the thief, the reason why you were caught, this is the reason why you were caught. And so the thief serves his time. He gets out of prison, and what does he do next? He's like, oh, I'm not the same thief who went to prison. I'm much better now. And he goes around and he creates new fake. And then it takes the police a while to figure it out, and then this game kind of continues. And at the end of the process, we have a thief that becomes really good at generating fakes, and a policeman that gets really good at telling these things apart. Hopefully, they don't spend all of their lives doing that, and at some point, they both shake hands and say goodbye with it. We don't know. And so the image you're supposed to see on the left is just the standard image of a GAN training. And so we start with random noise. And so the generator starts by generating really bad images, and as the training progresses, you start to see that it becomes really good at generating images. For some reason, there's some permission issues here. And so how did I kind of implement and run this experiment? I started with a DCGAN implementation using TensorFlow. And the main modifications I had to make was to write a custom input pipeline, essentially ensure that my curated image can flow through that network. And the second thing I did was to modify the generator and discriminator networks to generate 64px and 128px images respectively. So typically, that's just all about adding more capacity to both of these networks. And then finally, I ran all of these experiments on TPU. So the process is typically straightforward. The only challenge I had, which is more about my own mistakes, was that it turns out that the sample code for TPU implementations, it represents an image matrix in a really unusual way. And so typically, I would represent an image matrix by, let's say, the width, the height, and then the number of channels, let's say 64 by 64 by 3. But this strange code will do 3 by 64 by 64. And so what ended up happening was the first couple dozen experiments just outputted nonsense until I kind of hunted down that little problem and fixed that. And so what does it take to actually train a model on the TPU? And so the first thing you need to do is on the Google Cloud Console, you could log in. Hopefully you already have some access to a TPU. And you use this really nice command line tool that they designed called ctpup, and you will just run that. And typically it will walk you through the process of essentially setting up a compute engine VM to be used for the project. And typically that compute engine VM will be attached to a TPU pod or a TPU machine that's available. The next thing it will help you do is that it will help you SSH into that machine that is like that can access your TPU engine. Pretty much that's it. It's a straightforward process. And then finally, you could set your environment variables. Essentially, what I have here is my training script. Just the way you would run it on your local machine, you would run it exactly the same way. Essentially, you point to where your input data looks like, your model training parameters, and also if you wanted your training script to write its output to some storage bucket, you could specify all of that here. So it's an easy, straightforward process. So what are the pros and cons of actually using TPUs? The pros is that it's easy to set up. The second thing is pretty fast, and so it's easy to iterate and perform a lot of experiments when you use TPUs. And then final thing is it's available, and so I know there's something called the TensorFlow Research Cloud. How many of us here are students or researchers? Okay, and so the good thing is that I think for most of you, this is available for free. And so if you want more information on how to actually access them, I'm happy to have a conversation with you about that. The limitations here is that as of, well, recently, you need to rewrite parts of your code to actually run on TPUs. And so there's this thing called TPU estimators, and essentially you need to build your neural network and your training loop using TPU estimators. And so if you haven't used them before, your code wouldn't just translate and run automatically on the TPU. The good part is that with the release of TensorFlow 2.0, there's some work to finalize support for Keras models out of the box. And I think it's super close. I think the main challenge right now is that a lot of the TPU VMs do not have images that support TF 2.0 out of the box. But I think in the next month or so, you should be able to run Keras models out of the box on TPUs. And so at this point, I have this model that can generate 64px images. The problem is that in a high-resolution world, 64px is still super small. And if you try to generate something larger, 128 pixels or 256 pixels, you run into a problem that's a known problem with generative adversarial networks. It becomes really unstable to train, and it has some problems described as mode collapse. And so essentially, it's that a process where it just generates the same thing over and over again, and there's no diversity. And so the idea is, can we use neural networks, maybe some other type of neural networks, to kind of like solve the small resolution problem? And it turns out that yes, we can. And so you could use something called super resolution GANs. And the idea here is that it follows the generator and discriminator paradigm, but the idea is that instead of mapping input noise to generated images, what your generator tries to do is that it maps a low resolution version of your image to a high resolution version of the same image. And at the end of the day, G learns to super resolve input images, and D learns to distinguish between super resolved images from G and the original high quality images. And so it achieves this by using a perceptual loss, which is a combination of both the traditional adversarial loss and some kind of content loss. And I'm happy to talk about the details of this at some other point. And so at this point, does this really work? What do the results look like? And so I'll just flow through a few examples that I thought were really interesting. And I guess as an artist, if I was a good artist, I should name all of these pieces, but I haven't done that. So I guess that's one of the things on my to-do list. And so on what you see right now on the left is a 64 by 64 image generated by DCGAN. And on the right is a 6x super resolved version using another generative adversarial network, but this time from Topaz Labs Studios. And so the interesting thing to note here that there are details on the right that pretty much just don't exist on the left, but this model has been able to hallucinate or complete that image in a way that actually makes sense and it looks interesting. And this is another really cool example, and these things look like interesting artistic pieces to me. Well, I guess that's up for debate though, but they look really interesting to me. And so these are other examples, and some of my favorite examples. And I think I should have names for them. And so at this point, as a good research scientist, I have these really nice images, and I guess the thing that's on my mind is, are the images actually novel? Like, has the GAN actually come up with new African art pieces, or has it just memorized what's on the input network? And other questions are like, what kind of representations does the GAN learn, and how can we actually explore this space? And to kind of do that a little bit, I built a tool, something I'm calling an algorithmic art inspection interface. And what's here is that at the bottom, you see all of the images or some of the images generated by the GAN. And if you selected any one of them, it will show on the top the selected image. And on the right-hand side of that, it will show all of the images in the original data set that are most similar to that image. And it provides an interface to kind of compare, is the generated model just memorizing the input data set, or is it really doing some novel, interesting things? And the other question now is, how do you actually compute similarity? And so in some papers, some people will do things like pixel mean square between pixels. That's not a good idea. Another approach, which is what I actually use here, is to use features extracted from a pre-trained convolutional neural network. And so here I take 2 layers from VG16, an early layer that focuses on low-level features, its first convolutional layer, or the pooling layer after its first convolutional layer. And then I take also the last pooling layer. And I use both of them to kind of compute similarity and use cosine distance as a metric for that. And through these explorations, you start to learn a few things. The GAN has learned to generate oval images, masked with oval shapes. See that it learns masks with oval shapes, and sometimes it focuses on masks with like hair or hair-like projections. And this tool is actually available online on GitHub, so you can actually go and tweak around with it. And so finally, for reflections, I think one of the things I learned is that as this whole field kind of gets more proliferated, we're seeing neural networks actually generate art. I think it's important that we explore tools that help us tell, is this thing really novel? What's the visual quality like? And yeah, it's not just enough to generate these tools, but it's also important to find metrics and tools to evaluate its novelty. The other interesting thing is who has agency, right? And so let's say in a few years, the results of this process become really interesting. Who owns the IP? Is it me or is it the machine? And so my thoughts around that is that dataset curation is a careful process in which the artist can express themselves, and I think it's art. And parameter selection, what kind of model do I use? And there are a lot of strategies that artists can actually use here. It could be like training on one data set, having some pause, training a different data set, using different model architectures, and then finally interpretation and naming it. And so these are all ways in which the artists kind of express themselves and contribute to the process, and the model is just a tool. And then finally, there are important thoughts around ethics. So essentially ensuring that artifacts generated from the project are used in such a way that's beneficial and inclusive of its origins. It's also important to explore best practices around the ethical collection and distribution of the data set, and a few other emerging concerns that are out. Then finally, and I'm going to stop here, next steps for this project is we'll explore things like conditional generation. So there's some effort to kind of label this data set and explore conditional GANs. There's also effort to use unsupervised methods to explore interesting modes using things like infogans. Then there's efforts to improve the quality of generated images, and so optimizing the loss functions using things like variational autoencoders and their combinations with GANs. And then finally, some kind of interactive installation tool. There's a version of that online, but there's opportunity to kind of improve that. And so I'm at the end of my talk. The source code for training the GAN, you can find that there. And the interactive tool for inspecting novelty, you can find it in the second link. Thank you.